डियर स्टूडेंट्स, आज के लेक्चर में आप सबका वेलकम है। आज हम लोग डिस्कस करेंगे द प्रोसीजर ऑफ टू वे स्लैब डिज़ाइन इफ़ इट इज़ ए रेस्ट्रेंड स्लैब। रेस्ट्रेंड स्लैब हम उसको बोलते हैं जिसके कॉर्नर्स लिफ्ट नहीं करते, उसको हम टेक्निकली बोलते हैं द कॉर्नर्स आर हेल्ड ऑन। तो हम डिटेल में इस प्रॉब्लम को सॉल्व करते हैं। प्रॉब्लम स्टेटमेंट है, डिजाइन ए सिंपली सपोर्टेड टू ए स्लैब for a clear span 3.3 meter by 4 meter for a superimposed load of 3 kilonewton per square meter. Use M20 concrete and Fe415 steel. Wall thickness is 250 millimeter. Assume corners are held on. ये important conditions है टू वे स्लैब डिज़ाइन में, जो हमने इसके पहले एक प्रॉब्लम सॉल्व किया था जिसमें corners were not held on. So this condition is very important for two-way slab design. So we proceed with the design steps. If we take a dimensions of the slab, you can see here that the slab is having a width of 3.3 meter and the length of 4 meter. So the Ly is 4 meter and Lx is 3.3 meter. So this way the ratio of the span Ly by Lx comes 4 by 3.3, that is 1.212. So this is less than 2. So as per IS-456-2000, this is a type of two-way slab. So the first designing step, as we have done earlier in another problems, to calculate the effective depth of the slab. So as usual, as per IS-456-2000, page number 39, for given Fy 415 Newton per millimeter square, that is the tensile strength of steel, and the Lx value 3.3 meter, that is as per conditions in the code, this should be less than 3.5 meter, so it is okay. And the live load conditions should be 3 kilonewton per square meter, that is the load is given 3 kilonewton per square meter. The loading class is also satisfied as per IS code conditions. So we cannot assume the percentage of steel to proceed with the design. Let's assume the percentage of steel 0.4% here. So from this percentage of steel and from figure 4 at page number 38 of IS 456, we get modification factor 1.28. So putting this value as per the IS code guidelines at page number 39, we get LYD ratio, that is the deflection control criteria, LYD ratio equal to 35 into modification factor into 0.8. This we multiply because of the torr steel given, Fe415 steel grade. So this way we get this ratio 35.84. So from this ratio we can calculate the effective depth of the slab. So the given Lx is 3.3 meter, that is 3300 millimeter. So divided by this ratio 35.84, we get effective depth equal to 92.07, that is we may take a round value, that is 100 millimeter we can say. So by taking small d, effective depth equal to 100 millimeter, we can calculate the overall depth of the slab, total depth, that is 100 effective depth value, plus the diameter of the bar. If you provide 10 millimeter dia bars, then diameter 10 by 2, and plus a clear cover below the bottom of the bar 20 mm. So this way we get capital D 125 millimeter. So by this time we have got small d of the slab 100 millimeter and capital D of the slab 125 millimeter. Now the second step is effective span calculation. This also we have done in another case. So along Lx value, along the span Lx, we have, as per the IS 456-2000, page number 34, the first option is the clear span 3300 millimeter plus effective depth 100 millimeter, that is 3400 millimeter. And the second option is the center to center of the support. So the support thickness is 250 millimeter. So taking half from both the sides supports, so we get 3300 clear span plus the thickness of wall 250 millimeters, so that is 3550 millimeters. So the smaller value of these two comes effective span along shorter span is 3400 millimeter. Similarly, we get the effective span along longer span. First option, that is the clear span 4 meter 4000 plus the small d value along longer span is 10 millimeter less, because the center of the longer span steel and the center of the shorter span steel is separated by 10 millimeter. So we take a small d 100 minus 10, so that is we get 4090 millimeter. And the second option, the clear span plus thickness of the wall, that is 4250. So the smaller of these two is the effective span along longer span is 4090 millimeter. Now the third step is load calculation. So in the problem we have been given only live load. So from here we can first calculate the dead load, the self weight of the slab, that is the total thickness of the slab, depth of the slab 0.125 in meter, into the design width 1 meter we take, multiplied with density of concrete 25, that is 3.125 kilonewton per meter. Live load comes 3 into 1, that is 3.0 kilonewton per meter, and the floor finish comes 1 into 1, that is, this is given 1 kilonewton per square meter, multiplied with design width 1, that is 1 kilonewton per meter. The total actual load comes 7.125 kilonewton per meter. So if we multiply this by a partial safety factor for load, so we get factored load, the small w is 1.5 into 7.125, that is 10.6287 kilonewton per meter. So we have got the load also. By knowing the load, now we can calculate the mid-span moment for the middle strip of the slab, as we have already discussed the basics of the two-way slab, that the slab is having one middle strip and the side near the supports are known as edge strips. So in the middle strip, that is the mid-span moments along shorter span comes this we have to calculate according to IS code 456-2000 guidelines at page number 90 and 91. So here the ratio of Ly by Lx, that is the effective span ratio, 4090 divided by 3400 comes 1.2. So as per this ratio from the IS-456-2000 page number 91 and table number 26, we have already discussed that this is table number 26. From this table for restrained slab we get for Ly by Lx 1.2, and the problem says simply supported restrained slab. So this is a panel number 9, that is 4 edges discontinuous. So from this we get the alpha x 0.072 and alpha y 0.056. So we will use these two bending moment coefficients, and from this table we got alpha x 0.072 and alpha y 0.056. So from this we will calculate the maximum bending moment at the mid span along shorter span is alpha x w Lx square 0.072, w is 10.687 and 4.09 in meter whole square comes 12.87 kilonewton meter. Similarly along Ly longer span we get my, the maximum bending moment along longer span is alpha y w Lx square, so 0.056, 10.687 and 4.09 whole square, that is 10.01 kilonewton meter. So we have both these two moments, bending moments along shorter span and along longer span. Now the higher value of these two is 12.87. For this value we would check the effective depth, that is the safe depth for flexure criteria, and from this as per SP16 page number 10 table C we have already discussed, the effective depth is calculated for the mu lim, that is the limiting value bending moment. This will be equal to 12.87 into 10 to the 6 and divided by 0.138 FCK and B. So putting the values, taking the square root, we get small d 68.28 millimeter, and this is lesser than 100 millimeter what we have already adopted in this problem. So we are on the safer side and this is okay. Now we have to calculate the main steel area for the main span moments. So along shorter span, as we are doing the calculation of steel from SP16 table 2 for M20 concrete grade. So for the ratio we have to find mu by bd square 12.87 10 to the power 6 divided by 1000 divided by 100 square, that is 1.287. So from table 2 of the SP16 we directly get PT equal to 0.387%, and this percentage is more than the 0.12% for TOR steel Fe415 grade of steel. That is the minimum steel percentage required in any direction in the slab. So this is quite higher, so it is okay. So this way we can now find out the area of steel in sorted span is PT by 100 into BD, and putting the value we get 387 millimeter square. Now if we provide 10 millimeter diameter bar, as we have been discussing from another steps, so the center to center spacing of this bar would be 78.5 into 1000 divided by 387, and this comes 202 millimeter center to center for the main steel in the sorted span. So 10 mm diameter bar at the spacing of 202 millimeter center to center. Similarly, along longer span we have to calculate the value ratio mu by bd square for the long span bending moment. So 10.01 into 10 to the power 6 divided by b1000 divided by b1000 into 90 square, that is the small d in longer span, so 1.235. and from SP16 table 2 we get the PT value, percentage of steel, and directly we get 0.370%, which is again more than the minimum percentage of steel required in slab, 0.12%. so it is okay. Now the area of steel for this percentage in longer span comes 333 millimeter square, as we have calculated in the shorter span case. So for 10 millimeter diameter bars, center to center spacing comes 78.5 into 1000 divided by 333 and 235.7, which is round about 235 millimeter center to center we provide. So in longer span we provide 10 mm diameter bar at the center spacing of 235 millimeter center to center. So this way we have calculated the main steel into a slab as per the IS code guidelines given at page number 90 and 91. Now the most important step here is the design of torsion steel at corners, and the problem says that the corners are held on. We have already seen the problem. Assume the corners are held on, that is, as this is a simply supported slab, the slab is resting on the wall, but it is not a simple ordinary case. Here the corners are not allowed to lift, and for this purpose we have to provide extra steel at corners. That is, torsion steel at corners is according to IS-456-2000 page number 90 and clause number D1.8. According to this clause, we have to provide the torsion steel at every corner where both the adjacent edges of the slab are discontinuous. So here you can say all edges are discontinuous. So every corner have two adjacent edges which are discontinuous. So in this case we have to provide torsion steel at all the four corners. Now how we provide this? The length of the torsion steel at the corners would be Lx by 5. So we have the Lx 3400 divided by 5, that is effective span along shorter span. So this comes 680 millimeter. So from wall a length of 680 millimeter Lx by 5 from this direction and from this direction at all four corners, and the value of this steel would be calculated from the mid span main steel area, that is 387 millimeter square in our case in shorter direction. So the torsion steel area would be 75% of this area, that is 0.75 into 387, which comes 290.25 millimeters square, and this is for 1 meter design width of the slab. But again the point is here that the length of this reinforcement, torsion reinforcement, is only 680 millimeter, that is Lx by 5. So for this length we have to calculate how much area is required. So for 1000 millimeter to 1 meter we need 290.25 millimeter square, but for 680 millimeter length we need 290.25 into 660 by 1000, so this is 197.37 millimeter square. So this much area we need for torsion. Now If we provide 8 millimeter diameter bar for torsion, then the number of bars required will be 197.37 divided by 1 bar area 50.26, so that is around 4 bars. So in case of torsion, we need 4 bars at each corner in each direction, that is 4 bars like this and 4 bars like this. So one layer is 4 bar in x direction, another layer 4 bar in y direction, so all overlap and tied at every junction will form the top steel. Similarly, the bottom steel of 2 layers at bottom and 1 and 2 layers at bottom and 2 layers at top. So you can see here the 2 layers at top is shown by dotted lines and the 2 layers at bottom is shown by thick lines, continuous lines. So all 4 layers are provided at this corner, and this and this and this. So at all 4 layers we are providing the 4 layers of steel bars at each corners. So for each layer, let us say one layer each, that is the continuous line in this direction, another 2 layer is the continuous line in another direction, and same with the dotted lines at the top of the slab and continuous lines at the bottom of the slab. So you can see here for each of the 4 layers we need 4 bars. So 2 layers here, if we draw the cross section of the slab at AA as shown here in the plan, so you can find out that the main steel is something like this, continuous and bent up. So at the mid span we have 10 5 bars, 10 millimeter dia bars at 202 millimeter center to center, and the long span steel is shown here by the circles. So this is 10 mm diameter bar at 235 millimeter center to center, and near support it gets bent up. That in edge strip, the 50% of the mid span steel is bent up, which goes to the edge strip. As we've already discussed, near the support it is edge strip, and there we need the steel at the top of the slab. So the main steel provided at the mid span is bent up, which goes to the top of the slab in the edge strip. Now in near to the support we provide the LX5, that is from here to here 680 millimeter length of bars, that is 4 bars in this direction and 4 bars, that is the circles transverse to this. So both become forming a mesh at top and the same mesh at bottom. So these 2 mesh provided at the bottom and the top at the corner are the torsion steel, and this is similarly provided this side near the corner, this corner, and all in the back corners. So at 4 corners we have provided torsion steel according to the IS code criteria. The area of the steel is provided. Now suppose that if there is a corner and where only one edge is continuous, edge discontinuous, another is continuous, at that corner we provide 50% of the torsion steel as provided at such corners. So according to the situation in the plan of a building, the corner steel will be provided, and that is very important to restrain the corners from lifting, and that has so many other advantages in the slab. So with this I hope you have understood the design steps of 2-way slab and the design of especially the torsion steel at corners of the 2-way slab. Now various checks in this slab as we have done in the 1-way slab, so that are all similar steps. With this, thank you very much for attending this lecture.